Hello everyone, my name is Tatiana Gordeeva and I present to you my bachelor's thesis extending Weakesmo to infinite executions, under supervision of Anton Podkopayev. For starters, let's discuss what is Weakesmo. Weakesmo is a recently proposed weak memory consistency model that uses event structures to resolve the infamous out-of-thin-air problem and to enable efficient compilation to hardware. There was a lot of complicated words there, we'll look at each of them. What is a memory consistency model? Memory model describes the interactions of threads through memory and their shared use of the data. The consistency model specifies a contract between the programmer and the system, wherein the system guarantees that if the programmer follows the rules of operation memory will be consistent and the result of reading, writing and updating memory will be predictable. So what makes a memory model weak? A program is essentially a list of reads or loads when we look at a certain memory location and observe what is there right now, and writes or stores when we put a new value to some location of memory. Modern compilers and processors are really smart. They can perform a wide range of optimizations. One such an optimization is reordering, and a memory model tells us exactly what types of memory reordering to expect at runtime. A weak memory model may allow any of four types of memory reordering. Memory models try to provide some guarantees. For instance, data races freedom guarantee, which means that if we have no data races in sequential consistency executions, then we will only get sequential consistency behaviors. So, for example, we have a program where first we read from location x and y, then we also assume that initially these locations are initialized by 0, and then we have control dependency to some write. So for this program, in sequential consistency, the only outcome we could get is A equals 0, B equals 0. And actually in sequential consistency there is no data race. So for nice memory model, we would expect that it would allow only outcome of A equals 0, B equals 0. However, it is not the case, for example, for C++ memory model. It allows to get A equals 1, B equals 1 for this program. It is a well-known flaw of C++ memory model, and actually this flaw has a name. Out with thin air outcome. So if we want to have a data race freedom guarantee, we don't want to have an out of thin air, which is achieved in Weakesmo memory model. So how is it achieved? As you can see from the title, some mysterious event structures helped with that. Before we get to know them, let me introduce execution graphs. Vertices of execution graphs called events represent memory accesses due to the execution of program instructions. Each event is labeled with the type of the access, the location accessed, and the value read or written. Edges of execution graphs represent different relations on events. In the picture, three different relations are depicted. The program order relation totally orders events originated from the same thread according to their order in the program. An event structure represents multiple execution of a program in a single graph. Like execution graphs, event structures contain a set of events and several relations among them. Like execution graphs, the program order orders events according to each thread control flow. However, unlike an execution graph, program order is not necessarily total among the events of the given thread. Events of the same thread that are not PO ordered are said to be in conflict with one another and cannot belong to the same execution. Such conflict events arise when two read events originate from the same read instruction representing executions where the reads return different values. Event structures are constructed incrementally, starting from an event structure consisting only of the initialization events. Then, events corresponding to the execution of program instruction are added one at a time. We start by executing the first instruction of a program's thread. Then we may execute the second instruction of the same thread or the first instruction of another thread, and so on. When we establish a memory model, we want to be sure that it is valid and sound. Thus, we have to prove its compilation correctness. Compilation correctness of Weakesmo has been formally established in the article Reconciling Event Structures with Modern Multiprocessors. This proof is the first mechanized compilation proof of a weak memory model supporting sequentially consistent accesses to such a range of hardware platforms. The compilation proof goes with the recent intermediate memory model. The article shows the equivalence of these two memory models and checks it via COC, which then implies the compilation correctness of Weakesmo. However, this proof still has some drawbacks. One of them is that it relies on the assumption that program is finite. And of course, not every program is finite, and we'd like to know if infinite executions are also compiled correctly. It is particularly important for memory fairness research questions like how should an infinite execution be restricted in a weak memory setting, and when does a concurrent program terminate in this setting. We won't be able to investigate it until we are sure that everything is okay with our memory model. Thus, the goal of my work is to extend Weakesmo to infinite executions. To achieve this goal, I have to deal with several tasks. Firstly, I have to rewrite existing infrastructure so that it could support infinite sets of events. Then, this change of infrastructure will cause a lot of breakdowns of theorems, so I have to reprove lemmas and theorems via Coq. Then, I'll have to investigate which properties has to be added for Weakesmo to be valid under infinite executions. Because now it may lack some properties and not be compilating correctly under infinite executions. And when I will find these properties, I'll finally make the main theorem work and prove compilation correctness for Weakesmo. The latter two tasks are not still achieved, so I don't have anything to tell about them. Let's look at the first tasks. For example, when there is a finite set of acts, we have to define a function that labels our acts. Now we do not have an assumption that set is finite, so we just don't have numbers to name our infinite acts, so we have to deal with them the other way. We have to go to the set notation, and now we're not dealing with acts, we are dealing with sets of acts which are not used by now. And now we have to go to all the theorems that use this definition and fix them for the sake of correctness. So this is all I have for now. Unfortunately, I can't show you a GitHub as it is in private mode for this time. So thank you for your attention.